I have to.
Yes, on it.
So to get started with our graduate program, let me just pass the baton to Julie Bergner.
Hi, everybody. So we'll, like with the undergrad, we'll start with the awards. So we have a couple of graduate teaching awards. So we're very pleased once again to have one of our graduate students win an all-university graduate teaching award, which is a very great honor. This is chosen from all the grad students that teach across the university. And this year, Peter Johnson was selected for that. So let's give him a round of applause. And then we had two others of our grad students that we awarded departmental teaching awards to. And this year, these went to Andrew Will and Aaron Daw. So let's also give them a round of applause. Okay, so that's all for our awards. So then for degrees, so we had 3 students finish master's degrees this year. So I will read those off. So one is John Leonard Harnwar Jr., Jin Hanbyul Lee, and Stephanie Patricia Shand. I will add that Jin and Stephanie were 4+1 students, so they finished their undergraduate degree last year and have done an extra year in this very unusual year to get their master's degree. So congratulations to them. Okay, so now we continue with the students who finished their PhDs this year. So these are people who finished either last summer or in the fall or this spring. And so for these, I'm going to hand things over to their advisor to say a little bit about their work and what they've been doing. So the first of these is Christopher Kok-tik Chung, and who will be introduced by Wei-Chun Wang.
Thank you, Julie. Yeah, Chris Chung finished his defense later last summer. Okay, he's now a postdoc in Okinawa Institute of Science and Technology. Supposed to be a very nice place close to beach, and because of COVID, I haven't been there yet. So Chris wrote his dissertation entitled Quantum Coupling Group and Quantum Symmetric Pairs. And this subject lies in the direction of quantum groups, which was invented around 1985-86 by Greenfield and Jimbo, and Greenfield won Fields Medal largely because of that work. And it has much connection with math physics and representation theory and quantum topology, low-dimensional topology. And this variation of this, which is getting popular in the last few years, known as I-quantum group, arising from quantum symmetric pair. And this was introduced around 2000 by Gail Lester. And then it becomes increasing popular in the last few years. I will be very proud to say, largely due to a dissertation work by Huang-Chen Bao, who graduated from UVA 2015. Huang-Chen won AMS award because of his dissertation. So Chris worked in this direction and adding a little variation to this. And just like Lie algebra has a generalization to the Lie superalgebras by adding some suitable signs. And this quantum group turns out have a generalization, what we call the quantum coupling groups. For quantum groups, there's a quantum deformation parameter usually denoted by Q. Q stands for quantum. But for the quantum coupling group, besides of the parameter Q, this is one additional parameter, which we write as a pi. This is a very funny parameter. The square is 1. This is really a sign, but somehow when you write as a parameter, it's a shadow of some of these functors, which kind of represent a C grading shift. Just like the quantum parameter Q sometimes can be representing a C grading in some categorical construction. And so it's in this context, Chris wrote his thesis on the various structural results about quantum coupling groups. He discovered the so-called set presentation of this quantum coupling group. And this in this I version, this I quantum coupling group. He also constructed the so-called quasi-K matrix for this I quantum coupling group, which is a version of R matrix. And he further constructed the canonical basis of this I quantum coupling group, generalizing earlier work of Huang Bao in his 2015 UVA dissertation. So these are really, really nice work in a very active research area of quantum groups. And I think Chris is now here today, so congratulations to Chris. Thank you.
Thank you, Wei Chang. So our next PhD graduate is Bogdan Krstić, who will be introduced by Nick Kuhn.
Oh, let's see. Bogdan is, you can find him on a little square there somewhere. As I see he is there. He got his degree last summer. We spent a lot of time last summer and last spring, and I guess the winter before, on Zoom talking about his dissertation and writing it up. And so he got his degree last summer, 2020, and this past year he has been a postdoc, has a postdoc position at the University of Rochester, New York. So he's been channeling snow, things like this. So he came to us a number of years before that from Oregon State University. So his thesis title is called Bispans and Quasi-Categories. And where does this fit into? It fits into the world of algebraic topology and homotopy theory in particular. And what are these subjects? These are the subjects that are trying to understand global structure of geometric objects and maybe functions between geometric objects. And the word homotopy means sort of up to deformation. We do a lot of discussing mathematics where things can be deformed, but so you want to capture the things that are essential, independent of the deformations. So I guess in terms of his work, I had originally sort of pointed Bogdan when he was, through his first couple of years of reading a paper that I wanted to understand better and saying, why don't you figure out what this was? And we had a lot of chats about this. It was about something pretty specific about generalized characters of finite groups that were related to algebraic topology. And it was something I knew a lot about. And I sort of gave him the question, well, can we put this in some more general context? Can we relate it to some other things in the literature? And eventually he ran with this idea to a much greater extent than I expected. And he actually ended up working with things that I have very little familiarity with, these quasi-categories in technical sense. And I think he ended up with a theorem which is really, really interesting and really hopefully will become sort of a foundational theorem for people in this area. So I should mention some, let me just say a little bit. I thought I'd say a little bit about the words in the title of his thesis. So bispans and quasi-categories. Well, categories, perhaps, well, certainly a lot of our graduate students watching know what a category is, but maybe a few of the undergraduates do also. Category is a world in which you have things that you are studying and functions between those things. Okay, that sounds pretty sort of stupid when I say it like that, but if you to give examples, let me just point out things. It's sort of like almost a listing of undergraduate courses. Linear algebra is the study of linear vector spaces and linear functions between them. And calculus is the study of differentiable functions, and topology is the study of continuous functions, and group theory is the study of groups, and group homomorphisms are the functions. So this is a really common way of thinking about mathematics. And so that's what a category is. A quasi-category is something in which composition of functions is sort of deformed in some way that you really don't want to hear about on a Zoom chat right now. But one sort of keeps track of the messiness, okay? And they come up quite naturally and historically, mainly first from the geometric people, and then eventually the algebra people found they were interested in these ideas as well. My colleague Julie Bergner has written books about this, so it's quite fashionable thing at the moment. So quasi-categories, it's a world in which when you compose your functions, like f of g of x, it sort of like doesn't, it sort of deforms. So you have to figure out what you mean by that as well, and how you keep track of the information and not go crazy. So the other thing is, what is a span? It's bispans and quasi-categories. So a span is a word that somebody came up with. When you have a function, we all learned there's a domain and a range, and spans are, you play with situations where you have a function in each direction, a function from A to B and a function from B to A. And that's what spans are. And you can have fun how you would compose those things and things like that. So then a bispan has sort of two functions going from A to B and one coming back from B to A. And the A to B guys, you think of as an additive thing and a multiplicative thing. So, and it gets sort of complicated because you have to compare additive and multiplicative. So guess what? It's like a fantastic, complicated version of distributive law, because that was what you learned when you were in elementary school. The distributive law tells you how addition and multiplication interact. So it's a very high-end, sophisticated way of trying to build additive and multiplicative structures into these categories, and you've also deforming the versions of everything, and it's quite a mess. And but there was a good theory of spans and quasi-categories already, and in the literature. And I think with Bogdan's work now we have a good starting of a good theory of bispans. And the key idea, which is also relates to how people often do mathematics, was he knew what he wanted. And he was able to find that two guys in England had done some work where they looked at something sort of similar in a slightly simpler setting. And they had found, and he compares what he wants to this thing these guys did in England, which he had generalized himself. And the guys in England had something that was built so you could rip it into pieces and sort of solve smaller problems rather than solving everything at once. And you know, Bogdan thought hard about this for a couple of years and finally it all clicked together quite heroically. So maybe that's enough to say here. And I'm glad to see him here. And it looks like your beard and your hair are in good shape. Somebody's giving you a haircut. That's good to see. Oh.
Thanks, Nick. No haircut.
Okay. Good. Well, that's it. I'm handing it back to Julie.
Great. Thanks, Nick. All right. So our next graduate is Mark Edward Lewis, whose advisor is Yen Do, but I don't think it's either of them here. It doesn't sound like it, so I'll just read off his title here. So Mark's thesis was Carlson embeddings into weighted outer measure spaces. If we don't have anybody here to read that off, let's just give him a round of applause. And then I will hand it back to Nick, because our next person is Christopher James Robert Lloyd, who is also a student of Nick. So.
Okay, it's me again, gosh. Okay, and Chris is also, I think, on the Zoom somewhere. I've had a student this year finishing also. Chris, he is graduating, just has been graduating right now. And he came to us from a Virginia school, University of Mary Washington over there in Fredericksburg. And I'm happy to say it looks like he has employment, which is not so easy these days. Looks like he's going to be a postdoc at the University of Oregon. I say looks like because they're still processing funding paperwork and stuff. So his thesis is on a very different topic than Bogdan's. It's called Applications of Chromatic Fixed Point Theory. So let me give a little setting for his work. I'll say this fast and then I'll give an example. Suppose you have a finite group of symmetries acting on a geometric object. So here's a simple example. Think of a circle and flip the circle over, okay? And if you do it twice, you get back where you started with. So it sort of has the group of order 2 is acting on this circle, okay? So I said fixed point theory, okay. So if you have a geometric object like a circle or something else you can imagine, and some sort of symmetries like this acting on it, you could say what points are not moved at all by doing that, right? And that will form another object, a fixed point object. So for example, in the circle, I flipped it over, it looks like I would have 2 points that didn't move, okay? So you'd have, that's the fixed point object, happens to be 2 points, okay? So here's a very old problem, a really basic problem. How does the geometry of the fixed point object relate to the original object, okay? So for example, let me give another example with the circle. I could take every point to the point on the opposite side of the circle, and then the fixed point data is nothing. Nothing is, okay? So different, and again, if I do it twice, I get back where I started from. So you could ask, is there any connection between what I can get? So for example, could you get 1 point as a single point with a flip of some sort if you were just flippy enough or weird enough with your, how you, and so this has a famous, it's an old problem. And what's very fun for me is it has an old problem with really, really deep connections to math at the University of Virginia. And in particular, somebody you already heard a lot about from Christian Gromel, Ed Floyd. Ed Floyd, you might have been off by a year or two with when he been here. I think he was a graduate student here. He was a graduate student here, and I'm guessing, given the date that was mentioned, maybe from in the late 40s. I think he spent about a year or two at Princeton, and then he came back and was a professor here all from then on for his whole career. And as was mentioned, he, besides being a math professor, he was an administrator who eventually, when I was hired, he was in, I think, Pavilion 1 or 2, whichever one is to the right of the rotunda, when you look at the rotunda. And he was provost, he was still provost of the university. He stopped being provost of the university when I arrived in the fall of 1987. And I had a few years with him before he died of a heart attack. So this fixed point problem, there was early work in the 1930s, but in the 1950s, he and some other people also at UVA did amazing work finding weird examples and finding interesting examples of things you wouldn't expect. They have an example with a symmetry of order 6 on 7-dimensional space with no fixed points, and it was the smallest example, smallest dimension which you can find this happening. They're just really weird things these guys figured out in the 50s and into the 60s. He also developed the algebraic tools to study this problem. And so here we are now, really quite a while later. Chris's thesis title is Applications of Chromatic Fixed Point Theory. And chromatic is a word that represents sort of new tools that have been developed in my subject, algebraic topology, over the last 20 and 30 years. And lately, it's been sort of a pretty hot topic to study this fixed point problem, that I was saying, can you relate these things? So we first started with a joint project that I had, that I thought of, that was searching for really weird examples of things. And Chris found some examples. We had conversations, and then he'd go and he'd program every algorithm we had thought of on computers. And he found, by tapping into some group theory databases, some really interesting examples that people had missed who wrote some pretty fancy papers. So that was really fun. I think we sort of changed the story there with looking for oddball examples for these chromatic questions. But most of his thesis is sort of flipping the story here. We're starting with things where we understand the fixed point data very easily. And we're trying to learn something about this chromatic homology of some very much studied geometric objects. And these objects are called Grassmannians. Perhaps a few of you, well, perhaps a lot of graduate students know what this is, but some of the undergraduates might also. It's spaces of subspaces of space, like lines in space, projective spaces, things like this. And they've been important, really fundamental objects since the time of Gauss. And we have these very basic chromatic homology theories, and nobody has done any calculations, and we're running. So Chris has a lot of interesting work where he, again, had algorithms that he could look for patterns with his computer, and has some really fun things there. And I've never really had a student who used a computer so much and so well to find some patterns, and he proved some good theorems, general theorems, and make some really good conjectures. And it's a good thesis, and I think he has a bunch of fun problems to keep thinking about as well. And I think that's.
Thanks, Nick. Let's give Chris a round of applause. Okay, so next we have Ian Runnels, who will be introduced by Thomas Gaberta.
Great. So Ian came to us from Louisiana State University, and they were thinking mostly about mapping class groups of surfaces. So the mapping class group of a surface is, you have a two-dimensional manifold, usually with some finite genus and punctors or boundary components, and usually of negative Euler characteristic. And then you look at the homeomorphisms of the surface, and then you put an equivalence relation on them, where you say that two of them are the same. You can deform one into the other in a continuous way. So you can also think of this equivalently as the group of path components of the group of homeomorphisms of the surface. And so this object is very important throughout many different fields of mathematics, from algebraic topology, characteristic classes. In algebraic geometry, this is sort of it's the orbifold fundamental group of the moduli space of curves, and also in geometric group theory, which is the field in which Ian is now an expert. And they connected mapping class groups to right-angled Artin groups, which are this other class of groups, which is somehow very sort of simple to define. You take a finite graph, and you take a generator for each vertex, and then you just put one relation where you say the two vertices commute if the two vertices are connected by an edge. Okay, so these seem like very simple-minded objects, but they're actually, they're just as complicated as all finite graphs, at least, and they're a good sort of sandbox for testing many conjectures in geometric group theory, because they are sort of prototypical examples of things called cat zero groups. And they played a central role in the resolution of these various Thurston type conjectures in three manifold topology, such as the virtual Hawking conjecture and the virtual fibering conjecture. Now, mapping class groups have been around for a long time, for about a century, introduced by Dane, really. Well, maybe one could even trace it back to Klein. And it took, it was in fits and starts that the sort of theory of the mapping class group got developed. And Ian's concentration is in the algebraic and geometric structure of the mapping class group, the algebraic structure being sort of how it behaves as a group, and the geometric structure being sort of, if you view the group as a metric space itself, with sort of word length being the appropriate metric, how do the algebraic structure and the geometric structure interact with each other? Now, I told you the definition of the mapping class group, but it's kind of difficult to imagine how you might get your hands on any of the relevant algebraic structure. And there are even provable theorems like that. I mean, there's a result of Martin Brightson, which says that if you even look at finitely presented subgroups of the mapping class group, you can't, the isomorphism problem for that class of groups is unsolvable. They're extremely complicated. However, it turns out that if you sort of look at robust subgroups in some sense, you only get right-angled Artin groups back. So that is to say, if you start with finitely many elements in this mapping class group, and you say, I'm going to allow myself to replace these mapping classes by sufficiently high powers, and look at the resulting isomorphism type of groups that I get. And it turns out you always get a right-angled Artin group. And this is sort of very useful for proving things both about mapping class groups and for using mapping class groups to prove things about right-angled Artin groups, because right-angled Artin groups are these combinatorial objects, but then you can use sort of geometric realizations of them to be like, okay, well, now I can use my geometric intuition to prove things about this sort of combinatorial class of groups. So what was known is that there was just, if you had some finite collection of mapping classes, then there was some power that you could pass to, and you would get a right-angled Artin group. So what Ian did is they made the bounds explicit. Okay? And because the previously known proofs were that such a power existed were non-constructive, they relied on compactness arguments and other such tools that don't give you good bounds. It was difficult to have any sort of intuition about what the answer should be like. And so to be very specific about what Ian did is, if you consider, for instance, a collection of Dane twists, which are these very particular types of mapping classes, which are given by, you take a curve on the surface, which is sort of a embedded essential loop on the surface, and you cut the surface open and you reglue by a full twist. If you take a finite collection of such things, then you can just look at how many times the defining curves intersect each other in some when they're put in sort of minimal positions, so you can't simplify the picture in any way. Just from knowing that data, you can write down an explicit n. Just like you just write it down, and that's an n that works. So that's a very nice and explicit result. And so yeah, so that was one of the main results of their thesis. And yeah, and also in the course of proving this result, Ian developed some very nice ideas and tools for analyzing the geometry of something called the curve complex of the mapping class group, which is some way of organizing all the simple closed curves on a surface. Yeah, so now Ian will be going to Vanderbilt for a postdoc. So we're very excited to see what new results they'll be proving. So maybe we'll hear about some left-angled Artin groups at some point soon. So.
Great, thanks, Thomas. So let's give a round of applause to Ian. Okay, so next up we have George Henry Seelinger, who will be introduced by Jennifer Morse.
Hi, so I'm very honored and very excited about working with George and what George has accomplished, and to see him leave is a huge tragedy for me, but hopefully I can hunt him down to continue our collaboration. But his thesis is called K-theoretic Catalan functions. But it's a little bit deceiving because what's in his thesis was really only what he did the first couple of years. And after that, he's done like even better work. So it's, I don't know, I just can't really brag about him enough. But let me say a little bit about both of the things that he's been working on are rooted in symmetric functions. So symmetric functions are just polynomials, and that when you permute the variables, they don't change. And of course, they've been around for, you know, hundreds of years. But what's really interesting about them is that over 100 years of major developments in algebraic topology and algebraic geometry and representation theory, it's been discovered that you can explicitly look at a lot of the very abstract notions in those fields by connecting them to certain special symmetric functions, which again are just polynomials. So you can write them down and multiply them just like you always have been since you were little. So that's one thing that's turns out to be so relevant in this day and age when computing things, we're all about computing. And now this gives you a mechanism for computing things like, oh, I have this geometric object and this one, and I intersect them, and what do I get? And it turns out you can look at symmetric functions and answer these questions. And or if you look at representations and you want to look at how to decompose them into their building blocks, again, you can use computable symmetric functions to answer these questions. And of course, what is near and dear to our heart is that symmetric functions are supported by combinatorics. So basically you can play around with beautiful combinatorial objects like Young Tableau or Catalan paths, which is something that I see my undergraduate Evan was tortured with to no end in his class. So like lots of these combinatorial ideas help you to do things like multiply these polynomials, which in turn can give you the answer to these abstract questions. So what happens then is the questions that as algebraic combinatorialists, especially with our focus, is that our job is to kind of pin down like what are the special symmetric functions that we need to connect to modern day questions in, let's say, algebraic geometry for the sake of his thesis, but then representation theory for the work he did after that. Okay, and so one of the things that George did in his thesis was came up with a so-called Catalan function description for something that are called KK sure functions. Anyway, there's some geometric questions that people ask, and we wanted to know what were the polynomials that you could use to answer their questions. And the Catalan functions are a new tool, I guess, that came up recently. So as a graduate student, I was studying a bunch of stuff, and then for like 25 years, tried like crazy to prove some problems, and then finally made some headway with some of my co-authors using functions we call Catalan functions. But they're really just some huge class of symmetric functions that are defined by Catalan paths. Okay, and so that's why we called them that. And it ended up that by sort of looking at this really large class of Catalan functions, you had access to inductive techniques that you didn't have when you restricted yourself to the small family that you might have needed to really be looking at. And so in George's thesis, he goes further to define sort of inhomogeneous symmetric functions. Normally we're looking at polynomials all of a homogeneous degree, but he works on developing a theory where you now have inhomogeneous symmetric functions. And he proved, you know, using a combination, one of the sort of downsides if you don't really have all these wonderful qualities, but fortunately George did, but this theory, it kind of requires you to have like a computational mind, right? Because you have to like use the computer and look at polynomials and get data, but at the same time, you have to have a creativity to like invent a combinatorial structure to then define what you're seeing on the computer. And then you have to prove it all. So it's like really annoying because you have to be able to do like all those things instead of just being able to focus on like, oh, I'm really good at the computer, or, oh, I'm really good at proving things. And what's wonderful about George is he's actually really good at all of those things. And so he was able to, you know, use the computer and come up with really, you know, nice combinatorial identities and then prove these polynomials are actually the ones that are connected to the geometry. And that was kind of his thesis. And then since then, we're like now involved in kind of a collaboration that has just exploded. And this is connected to something called Macdonald polynomials, which again are just symmetric polynomials, but they came about, you know, in the 80s when everybody was like spicing things up by looking at quantum deformations of whatever your field is by putting a Q in and saying it's quantum. And so in symmetric functions, we put Q's in the coefficients instead of numbers and said like, these are quantum symmetric functions. Okay, but anyway, so Macdonald polynomials are examples of these, and they've been discovered to connect to like all sorts of different fields, analytic, algebraic, geometric, everything. And so there have been some problems though that have been open since the 80s. And so of course that's basically my personal obsession, and I think now George's, is to think about these problems. And so in this group that we have, we did prove some of those outstanding conjectures, and there's still like some more to do. But I guess the point is that he's going to the University of Michigan is where he got a postdoc, which is not only like an amazing place in his field, it also for his personal life was exactly where he wanted to be. And so I just can't, it's like the university, he's my first PhD student at UVA, right? And like, if I thought the university cared this much about me, I would be sure that they like planted him here as my student to make sure I never left. Like, this is what the students look like, right? It just seems like unreal. So I really, really, really lucked out. And I feel like being at UVA has definitely been improved by having George as a graduate student. And now I'm happy he's going to Michigan and he has loads of problems, not just in the collaboration that we're probably going to continue, but at the same time, there's other problems with the geometry that he worked on his own and put in his thesis, like without my saying anything. So he has, in addition to all those other things, like hardworking and like initiative, and he's also like really polite, which sounds like a weird thing to say, but I'm always like thinking, God, why aren't my kids like this? Like, I know he's not a child or anything, but I definitely hope my kids grow up to be somebody like George, because it would be so great. So anyway, I really want to congratulate George and like just thank the department also just for bringing him here. He was a Jefferson Fellow, and that was the right move on the university. So anyway.
Great, thanks, Jennifer. Let's give George a round of applause. And last but not least, we have Laosha Shu, who will be introduced by Zoran Krujic.
Hey, thanks, Julia. So so Lyosha graduated in December of last year actually, and he's currently at MSRI at the Mathematical Sciences Research Institute. There is a program of mathematical fluids, and so he's holding a fellowship now there, and I can see him in the corner here. Hi. So basically, let me say a few words about the topic. So the title of his dissertation was, I guess, several topics on the Navier-Stokes problem. And so, so the Navier-Stokes equations are basically, they're a fundamental model for the study of fluid flows, right? And especially incompressible viscous flows like, usual fluids, right? Water, air that's not too thin, I'd say, oil, anything sort of, when you think about the normal fluid, not like a super fluids, kept at, 0 temperatures and things like that, right? And so basically there is this, there are two things that Navier-Stokes equations are supposed to describe, right? One is just, it's a basic PD model for the behavior of the fluid flow. So you can ask the standard questions as you ask for like, any kind of differential equations, even in like, ODS 3250, right? So existence, uniqueness, stability of the solutions, right? And the other thing is they're supposed to be mathematical model for turbulence, right? So this is kind of little bit distinct because turbulence theory, it's more like statistical theory, it's phenomenological. Mathematical theory of turbulence, it's really not developed that great still, even to this day, right? And so these equations are kind of dual thing, and these two things are quite connected. Just the question of whether a singularity can form in the system. On one hand, it's like a typical PD problem, right? At the other hand, it's just like to connect it to the actual phenomenology of turbulence. And so physically, what's happening? There are these two key mechanisms basically trying to balance each other, right? So there is diffusion in the system. And so that's a linear mechanism. So diffusion forces tries to dump down the nonlinear effects, and there is nonlinear transport of energy. And if you take any beginning book in turbulence, it's going to talk about the energy cascade, right? This is this big principle that Kolmogorov quantified, back in the 40s. So you have this. Imagine some sort of energy containers, right? So imagine like a waterfall, right? So there are big chunks of water that disperse in the smaller and smaller until they're really small and everything gets dissipated and into heat and disappears basically, right? As long as you don't pump in additional energy in the system. And so this is like, essentially what mathematically, we're trying to figure out, right? The precise, interaction between diffusion and this nonlinear turbulent cascade, right? It's like purely nonlinear effect, right? And so, so Lyosha has basically during his graduate time, he wrote 5 papers in this field, and I would call them 3+2 because the first 3 were already, more than enough for competitive thesis. But then we got in this other +2, and then I kept him here for a while. But yeah, so the first 3 papers, I would just say his solo paper was basically, it's in mathematical terms, right? So we need functional spaces to be able to deal with PDs in some concrete ways. And so, what was basically known in the space of bounded functions, right? But the only thing that matters is the absolute size of the physical quantity, either velocity or vorticity. He basically proved the result in the space of comparable result about the Navier-Stokes in the space of bounded mean oscillations. So that you don't look for the absolute size of the field, you just look how much the field fluctuates from the mean. And this is exactly what you care about in turbulence, right? You care about the size of the oscillation of the fluctuation. You don't care about what basically absolute size of the thing is. And so that was actually open problem in the field, and it was really a great result already back then, a few years ago. So that was one thing that I'd like to mention. And then this +2 thing. So there are 2 papers. So this is joint. We're working on this together. But basically, so what happened as far as studying singularity goes in Navier-Stokes is that since 60s, in a way, there is this what we call scaling gap, right? There is this abyss between what we can mathematically prove and what it's needed to rigorously rule out any singularity formation. And people in the field pretty much almost settled on the idea that we call the supercriticality in terms of mathematical physics type of words. And most, it's not maybe most, but lots of people in the field already settled on the idea that this Navier-Stokes problem is supercritical. And so what these two basically papers show is that it's not, right? That it's what we call asymptotically critical, that you can close this abyss as close as you want, right? You can't really get exactly to what you want because they'll have this $1 million already and be out celebrating. But it's there is no conceptual problem, right? There is an abyss between things. There is a conceptual problem, and this is saying basically you can get as close as you need to what you really want. And it's not in any scenario, but it's actually in the turbulent scenario, right? The one that's the most interesting from the perspective of fluid dynamics, right? And so there are rigorous proofs for this now. And since it's a joint work, what I really want to say is that I had some sort of general setup for this for years. I was playing with this in the sand, 7-8 years ago, and then with my former students and postdocs. But this whole the main actual thing about how to quantify the energy cascade in this setting, like transfer of the energy different levels, how to actually track down the non-linear interaction in the rigorous way, that's all Lyosha's work. I mean, this is it's impressive. I mean, this is what people really try to do since 60s, and there was no setup to do it. And it really is his thing, when we started this, he really has this very elaborate way how to track different levels and how to study this cascade process, increasing, decreasing, and all of that. So yeah, I mean, I'm just it's puzzling to me that this actually works, right? I think it's gonna take a couple of years for this to actually properly filter out in the community, honestly. But all I guess want to say is that the most difficult part by far of this joint work, it's really his work. I was kind of just looking, so yeah, that's it's beautiful, really. I mean, it's just pretty, basically. Okay, so yeah, that's my story, and it's all on the board there, and I can also talk about it for next 3 months, but you probably don't want me, so I'm just gonna stop here. And congratulations, Lyosha, it's really great work. Yeah, thank you.
Great. Thanks, Soren, and let's congratulate Lyosha. And maybe just one more round of applause for all our PhD graduates. And then I guess I will turn it back over to John to wrap up. You're muted, John.
Thanks so much, and congratulations again to really a remarkable group of graduates, and having done really remarkable work. So I wish them all great success in their next endeavor. And with that, I guess we can close the meeting, and we'll see you next year.